Hi, today we are going to talk about statistical inference about multiple regression case. So statistical inference implies either hypothesis testing or confidence interval. So simply you can, in this course, we only have two methods. So let's think about the hypothesis testing in the regression with multiple regressors like this. So this is a very general regression model where you include 1, 2, k regressors. So, but in this case, let's start from the simplest possible case where you are interested in only one of them. So you are interested in only one, say x1, and the other guys are simply control variables. So you don't care what beta 2 is, what beta k is, but you are interested only in the coefficient of beta 1, like the coefficient of student-to-teacher ratio. And then suppose that in hypothesis testing framework, you'd like to test a null hypothesis about a single coefficient. For example, like this. The null hypothesis is given as beta 1, the coefficient. You believe that the coefficient equals to beta 01. So beta 0 is a specific value for beta 1. And then how can we test it? So you believe that beta equals to beta 0, but from the data you have a different estimate. So you are comparing what the data tell you and what your belief tells you. So the t-statistic, we measure the difference by a t-statistic. The t-statistic is defined as the estimate, which is from the data, and beta 0, which is from your hypothesis, and take the difference. So how different they are. It captures the difference, but it is also standardized by the standard error. So because the estimator may have some errors, so you have to standardize. So you have to capture the relative size of the difference considering the potential error. So this measures the standardized difference between the data and the hypothesis. Of course, if the difference is too large, then your hypothesis is likely to be wrong. But when the difference is small enough, then your hypothesis is consistent with the data. So our decision rule is, our decision about the hypothesis is made based on this rule. So if the t-statistic is too large, when I say too large, it means it is outside of plus minus 1.96. So it could be greater than plus 1.96 or smaller than minus 1.96. So either way, so the estimate is too large or too small relative to the hypothesis. So then at this threshold, if we say that the null hypothesis is rejected at 5%, at the significance level of 5%. And the most common hypothesis testing is based on this assumption. So this hypothesis. So like maybe the starting point of the analysis is to see whether there is any significant effect or not. So if you cannot reject this, so this means student-to-teacher ratio has no meaning, no effect. And then if this cannot be rejected, then your regression has no meaning because you are looking at the effect of student-to-teacher ratio, but it turns out to be 0. So then nothing can be said. So it's simply 0. So your data don't have any relationship implied by the regression model. So this is maybe the first question you have to think about. And then so this is hypothesis testing, and this is confidence interval from the same setup, multiple regressors. We are interested in beta 1, and then beta 1, you have 1 point. That is a point estimate, but a point estimate cannot be correct. It is wrong all the time. So you have to allow a certain margin of error. the margin of error is also given by 1.96 times standard error. So they are closely related. T-statistic has standard error in the denominator, and compared with plus minus 1.96, the same guys are used again. So in this sense, the confidence interval and hypothesis testing are kind of parallel. They are quite similar to each other. So then it'll be, this confidence interval will be an interval, not just one number, but it tells you about the potential interval where the truth will be. And this is confidence interval with 95% confidence level. So 95%, it must be correct with 95%. By the way, then if you understand this is correct with 95%, then you can interpret this 5% means your decision could be wrong with 5%. So your rejection could be wrong with 5%, and also that is equivalent to 95% confidence level. And so far I quickly summarized how you can conduct statistical inference if you are interested in only one coefficient. Even if there are multiple regressors, there is no difference. So like when you focus only one variable, then the analysis is exactly equivalent, identical to what you have done for the regression with one variable. So it is about how many coefficients you are interested in, not about how many regressors you include in the regression model. And also, you can see that in this calculation and in this calculation, what you need is only the estimate, beta hat, and the standard error. So if you have beta hat and standard error, and if you use the standard significance level or confidence level, 1.96 does not change. So this is fixed. So as long as you obtain those numbers, estimate and standard error from Stata, then you can calculate the t-statistic and the confidence interval by hand. So it is quite simple, but still Stata also calculate these for you. And as I said, there is no difference. So simply speaking, there is nothing to worry about if you are interested in one coefficient. So like for example, in our example, if the test score, whether you regress test score on student to teacher ratio only, or whether you regress the test score on student to teacher ratio and another control variable, it doesn't matter. You are only interested in this guy, the effect of student to teacher ratio, and as long as you have the estimate minus 2.28 and the standard deviation 0.52 or minus 1.1 and 0.43, then you can calculate the hypothesis testing or the confidence interval. Just it is up to you which model you are taking. I would use this one because control variable will reduce the omitted variable bias. So I would use this one. Then based on this, apply the same procedure for hypothesis testing and confidence interval. From Stata, if you use Stata, and suppose that we are using robust standard error formula, so it's simple, just put robust option here, then robust standard error is calculated. It does not change anything. All the procedure works in the same way. So you have a coefficient estimate and robust standard error. Use these two guys to calculate t-statistic. Already t-statistic is calculated based on this formula using this specific value. So assuming that your hypothesis is about 0, then the t-statistic will be calculated by this. This is the difference between your coefficient and 0 standardized by the robust standard error is minus 2.54, which is outside of plus minus 1.96. Therefore, your coefficient is statistically significantly different from 0. That is what we can tell at 5%, by the way, at 5% level. Or you may consider the confidence interval. 95 confidence interval is calculated in the same way based on this estimate and this standard error. Then the confidence interval is from minus 1.95 up to minus 0.25. So all the interval, any point on this interval is a negative number. So according to the 95% confidence interval, the effect of student to teacher ratio is negative. So it is not 0 or neither positive. So also it gives you the same idea. As the effect of student to teacher ratio is statistically significantly different from 0, and especially it is negative. So that's how we conduct statistical inference on a single coefficient. So there is nothing to worry about, but we are going to extend our procedure if you are interested in multiple coefficients at the same time. For example, we include another important variable of our interest, say expenditure. So it is the expenditures per student, and we are going to consider a regression model with 3 regressors: student to teacher ratio, and expenditure per student, and percentage of English learners. So then, if you consider these 3 variables, we are still interested in our variables of interest are student to teacher ratio and expenditure at the same time. So we would like to see whether hiring more teachers would be better, or just giving the school more money would be better. So we would like to, for example, compare 2 different policies, or we'd like to see what is the optimal combination of them, or whether if any of them has any effect or not. So these 2 variables are of our interest, and the third one, percentage of English learners, is still a control. It is important to be here, but we are not going to interpret beta 3. Beta 3 is not a big of our interest. It does not draw our attention at all. So then we would like to test whether beta 1 and beta 2 have any impact or not. So beta 1 equals to 0 and beta 2 equals to 0. So this null hypothesis means both of the variables have no impact at all together. So they neither has any impact on the test score. So if this null hypothesis is not rejected, that means you don't need to spend any money on the school, and it has no impact on the test score, at least. So like any expenditure, any investment on students have no impact on the test scores. So we would like to reject it to say something. So we are going to test it, but its test is not straightforward. We need to extend the previous framework because we have to think about 3 alternative cases. So negation of this statement is either beta 1 is non-zero, or beta 2 is non-zero, or both are non-zero. So if one of them is wrong, then the whole statement is wrong. So we have to think about these 3 cases, and we will think about how to handle this. Okay, I'll continue in the next one. See you later.